today, and our next speaker is Jiang, who is postdoc at mathematics, and his talk is about Terwilliger F-algebras of quasi-thin association schemes. So, Jiang, the floor is yours.
Okay. Firstly, I thank Professor Elena for introducing me. Now, the title of my talk is Terwilliger F-algebras of quasi-thin association schemes. Firstly, let us collect some known definitions. Most definitions are from Professor Jiang's book. Firstly, let us recall the definition of an association scheme. Here, our association schemes may not be commutative. Definition 1.1, let X be a non-empty finite set. Let S be a partition of the Cartesian product X cross X. Here, elements of S are written as R0, R1 to RD. Then S is a scheme on X if we have the following three conditions. Condition 1, R0 is just the set of pairs XX where X is in X. Condition 2, for any RA in S, there exists RA prime of element RA. Condition 3, for any RA, RB, RC in S, and pairs XY, X tutor, Y tutor in RC, we have the following equation. The equation says that the concanatality of the set here is equal to the concanatality of the set here. Here, we know that the constant here only depends on our PABC. Note this constant non-negative integer called PABC, the intersection number of S with respect to RA, RB, and RC. Next, we recall the definition of valency, the definition of complex product, and the definition of quasi-thin scheme. Definition 1.2, let S be a scheme on a non-empty finite set X whose elements are R0, R1 to RD. For any X in X, let XRA be the set of all Y in X such that the pair XY is in RA, and we note that the concanatality of XRA equals PAA prime 0, which is strictly larger than 0. Let KA be PAA prime 0 and call it the valency of RA. Let U and V be two non-empty subset of S. Then the complex product of U and V or elements RA such that there exist RB in U, RC in V, PBCA strictly larger than 0. For any A, B from 0 to D, let RA times RB be the complex product of singleton subset RA and the singleton subset RB. From now on, we fix a non-empty finite set X and a scheme S on X. Here, elements of S are written as R0, R1, RD. We also fix a field F of characteristic P larger than or equal to 0. So P is either prime or 0. Next, we can support the following definition. Definition 1.3. the scheme S is quasi-thin if Ka less than or equal to 2 for any A from 0 to D. The scheme S is thin if for any A from 0 to D, K equals 1. So from the definition, we know that any thin scheme is also a quasi-thin scheme. We also need the following definition. Definition 1.4, let MXF be the full matrix algebra of square F matrices whose rows and columns are labeled by elements of X. Let EXY be the matrix union in MXF whose unique non-zero entry is in the XY position. For any A from 0 to D, the adjacency F matrix with respect to RA, denoted by AA, is defined to be the sum of all EXY, where the pair XY runs over RA. Let X be in X. Then the dual F idempotent with respect to X and RA, denoted by EA star X, is defined to be the sum of REYY, where Y runs over XRA. Next, we will introduce the main research object of the talk. Definition 1.5. Let X be in X, the Terwilliger F-algebra of S with respect to X, denoted by Tx, is defined to be the unital F subalgebra of MXF generated by A0, A1 to AD, E0 star X, E1 star X, ED star X. If we specialize F to be the complex number field, then the Terwilliger C algebra of S with respect to X is exactly the usual Terwilliger algebra of S with respect to X. So the notion of Terwilliger F-algebras of schemes slightly generalized the notion of usual Terwilliger algebras of schemes. Next, we will introduce some motivations of our work. Motivation 2.1 in the paper, modular Terwilliger algebras of association schemes. Hanaki illustrated that the Terwilliger F-algebras of S may not be semi-simple. He also showed that Tx is semi-simple only if for any A from 0 to D, P does not divide Ka. Unfortunately, he also illustrated that the reverse of his result is not true in general. So even if we may have for any A from 0 to D, P does not divide Ka, it cannot let us conclude that the corresponding Tx is semi-simple. There are some counterexamples. Next motivation, motivation 2.2. This motivation is also from another paper, survey of semi-simple algebras in algebraic combinatorics. In this survey paper, Hillman says that the study of the Terwilliger F-algebras of S is almost completely open if P is a prime. The above two motivations are somehow high level. I will give a more direct motivation. Motivation 2.3. This motivation is from an easy example. So here, if S is a thin scheme, then it's not a Terwilliger F-algebra of S with respect to a given vertex X is equal to the full matrix algebra. So in this example, the structure of Terwilliger F-algebra is easy. So we want to ask this question: how about the Quasi-thin case? It's reasonable to consider that the Quasi-thin case is also not very difficult. Next, we will present our main results. Firstly, we are interested in the F dimensions of Terwilliger F-algebras of Quasi-thin schemes. We will need the following definition 3.1. We let Ri0, Rg0, Rl0, Ri1, Rg1, Rl1, blah, blah, Ria, G, L, Rla, be a sequence of S, where A is a positive integer. Then the pair I0, La, the index here, is called a bad pair of S if the following two conditions hold. Condition 1, we require that KIB and KLB are all2 and PIB, GB, LB equals 1 for all B from 0 to A. Condition 2, we require that the concatenality of the complex product Ri0 Rla equals 1 and Lc equals IC plus 1 for all C larger than or equal to 0 and is strictly less than A. We will use two examples to demonstrate definition 3.1. These are our examples. Example 3.2. So here, if S is a scheme of order 28, number 175 in the database constructed by Nike and Miyamoto, then we can read the corresponding data from the web page. So D here equals 15, K4, K7, K9, K30, K8 are 2, and P479, P938. The concatenality of the complex product R4 R8 equal 1. Then we consider the sequence R4, R7, R9, R9, R30, R8. And we know that the pair 48 is a bad pair of S because we can check condition 1 and condition 2 hold for this sequence. Next, if S is the scheme of order 6, number 5 in the same database, then by data, we have D equals 3, K0, K1 are 1, and K2, K3, the concatenality of the complex product Ra prime Rb are all 2 for any AB from 2 to 3. In this case, we use this equation in condition 1 and this equation in condition 2, and the given data, we can conclude that there is no bad pair in S. Now we are ready to give the main result here. Theorem 3.3 assume that S is a Quasi-thin scheme, then the F dimension of Tx equals the sum of d plus 1 to the power 2, the concatenity of this set, and the number of all bad pairs of S. So we somehow determine the F dimensions of Terwilliger F-algebras of Quasi-thin schemes. We can give the following remark. Remark 3.4. By definition 3.1, the definition of a bad pair of S, we know that the bad pairs of S only depend on the intersection numbers of S. In particular, theorem 3.3 tells us that the F dimension of Tx only depends on the combinatorial structure of S if S is Quasi-thin. For the journal case, Hanaki illustrated that the F dimension of Tx may depend on P and the choices of X. So it means that for the journal case, it seems to be very complicated and uncontrollable. So far, we don't have a lot of good results for the journal case, but we can still see something. We use the following remark to see. So remark 3.5. In this remark, S is assumed to be an arbitrary scheme. In this case, the F dimension of Tx is no less than the sum in theorem 3.3. So if we combine theorem 3.3 and remark 3.5, then we give an optimal lower bound for the F dimensions of Terwilliger F-algebras of arbitrary schemes. Next, we consider about the semisimplicity of Terwilliger F-algebras of Quasi-thin schemes. Our main result is as follows. Theorem 3.6. Again, assume that S is a Quasi-thin scheme, then Tx is semi-simple if and only if P does not divide K for any A from 0 to D. So this result tells us that the inverse of Hanaki's result is also true for Quasi-thin scheme case. Moreover, we can determine the semisimplicity of Terwilliger F-algebras of Quasi-thin schemes. As we are studying the semisimplicity of finite dimensional associative algebras, we want to study the corresponding Jacobson radicals. The result about Jacobson radicals are as follows. Theorem 3.7. Here, assume that S is a Quasi-thin scheme. We let G be the all-one matrix in MXF. Then the Jacobson radical of Tx equals the F linear space generated by the set here. In this set, elements is EA star X, GEB star X. The matrix matrix product. Here, the condition is P divides the product of Ka and Kb. Again, determine the Jacobson radicals of Terwilliger F-algebras of arbitrary schemes is very difficult. So far, we don't have a very good result, but we can still say something. We use the following remark to see. Remark 3.8. So in journal, here in this remark, S is also an arbitrary scheme. So in this case, the F linear space generated by this set. So the same set as here is a nilpotent two-sided idea of Tx. So in particular, it's an F subspace of the Jacobson radical of Tx. So if we combine this result, theorem 3.7, and this remark, we somehow give an optimal lower bound for the Jacobson radicals of Terwilliger F-algebras of arbitrary schemes. Finally, we want to study the algebraic structures of Terwilliger F-algebras of Quasi-thin schemes. Our main result is theorem 3.9. So here, assume that S is a Quasi-thin scheme and is not a thin scheme. If S is a thin scheme, then we know that any Terwilliger F-algebras of S is just a full matrix algebra. Now we define AI to be the set of elements A, here A from 0 to D, and Ka equals I for any I from 1 to 2. We let sim be the binary relation on A2, where for any A, B in A2, A and B have such relation if and only if the concatenity of the complex product RA prime RB equals 2, or the pair AB is a bad pair of S. We can prove that sim here is an equivalence relation on A2. As sim is an equivalence relation on A2, we can set C0, C1 to CL be all pairwise distinct equivalence classes of A2 with respect to this sim. We also let M and F be the usual full matrix algebra of n-cross-second matrices whose entries are in F. Then we will have the following two statements. Statement 1, if P is not 2, as F algebras, Tx is asymptotic to an algebra A, direct sum with F from 0 to L, M, the concatenity of Ci, F, where A is a simple F algebra with F dimension D plus 1 to the power 2. Here, we cannot write the form of A neatly because we don't assume that F is an algebraically closed field. So it's not, we cannot easily use Wittbond-Arding theorem in this case. We know that A is asymptotic to some matrix algebra, but we don't know the coefficient ring. Here the coefficient ring is F, but for this algebra, we don't know the coefficient ring. Next statement, if P equals 2, let Gx be the Jacobson radical of Tx. Let Tx over Gx be the quotient F algebra of Tx with respect to two-sided idea Gx. As F algebras, we have Tx over Gx. This is a quotient algebra is asymptotic to M, the concatenity of A1 F, direct sum with F from 0 to L, M, concatenity of Ci F. So for the case P equals 2, the structure is somehow clear. We will give several corollaries about theorem 3.9. Corollary 3.10. In this corollary, we assume that F is an algebraically closed field and P is not true. Assume that S is a quasi-thin scheme and is not a thin scheme because we don't want to consider about the trivial case. Then we get the following equation. So Tx is asymptotic to md plus 1 F, direct sum with F from 0 to L, and concavity of CIF as F algebras. Corollary 3.10 is from the first statement of theorem 3.9 and the Wittmann-Ardeen theorem. Because in this case, we assume that F is an algebraically closed field. So A tends to be md plus 1 F, just Wittmann-Ardeen theorem. Next, we will consider about another corollary. So corollary 3.11. Assume that S is a quasi-thin scheme. If S is thin, then Tx has a unique irreducible Tx module up to isomorphism. On the other hand, if S is not thin, then the number of all pairwise non-isomorphic irreducible Tx modules is L plus 2. Because we have determined the algebraic structures of Terwilliger F-algebras of quasi-thin schemes, we can read from the structure that the number of all pairwise non-isomorphic irreducible Tx modules. Finally, we conclude our presentation with the following question. So question 3.12. In this question, we want to find the algebraic structures of the Terwilliger F-algebras of some special schemes. Because for the general case, according to Hanaki's results, the general case seems to be very complicated and uncontrollable. So we think that some special schemes, for example, some special symmetric schemes. That's all. Thank you very much.
Okay, thank you very much for your talk. Are there any questions to the speaker?
Yeah, I would like to ask a question.
Yeah, sure, please, Aaron, yeah.
Jan, can you please go to 3.6?
3.6 is here.
Ka is the valency of Ra, right?
Yes, K is the valency of Ra.
So does this just mean that Tx is semi-simple if and only if P is odd?
Yes, yes.
Oh, okay, good. Yeah.
P is odd and P equals 2 and S is thin. S is thin scheme. Two cases. I just combined the two.
Yeah. So I just want to make sure that I understand that correctly.
Into,
right.
One sentence. I mean, it's right. I mean, yes, correct.
Yeah. Are there? I have two more questions. One more question and a comment. Are there people who try to give sufficient conditions for the converse of Hanaki's result? Apparently, the converse is not true, but
yes.
There might be a criterion which says if and only if.
So according to my knowledge, so far there are no such sufficient condition. I mean, according to my knowledge,
okay.
I don't know.
And last comment, are you aware of the papers by Myzychuk and Ponomarenko about quasi-thin schemes?
Yeah, I know this paper, and
okay, good. Yeah, maybe there's some information which might be helpful for your. Thank you.
Thank you very much, Professor.
Okay, thank you very much for questions and for the nice talk, interesting talk. Now we finished for a time.